Yeah, when I was a student, I always wonder why the professor keep unable to do things. Yeah, now turn out I'm one of the teacher, and actually I have technical problem because I thought I was a guy who is able to handle technical issue, but turn out that something when the fundamental system is flawed, then no matter how good you are, then you can't really work because you need the lock to unlock the stuff. But anyway, so just I think we talk about the how to define an extensive form game, and do note that although this is a formal way to write this thing, when you never write in this way in your paper, right? So basically what you are going to do is verbal description, and so that means that you have to be very careful. Make sure your verbal description contains all the elements. Okay, so that is the key here. It's not learning how to define this thing, rather is make sure that your verbal description, your model, is complete enough that people can fill in this space if they ask you to fill in. Is that clear what I'm saying? It's not you know how to unlike the normal form game, you probably have to define it carefully. What's a player set, strategy set, and payoff function? But here is you have to be very careful. Make sure that the all these things is well defined in your setup, right? If you try to describe this game, it's rather simple, right? Basically, just like one player in the first round show his coin, head or tail, and second stage is player two seeing what player one have chosen. Player two decide what to do, and the payoff is given if both are the same side. Player one get $1. If they're different, player one lose $1. Right? It's a zero-sum game, right? So that is how you define this game, right? In verbal, okay. But the verbal thing is actually a very clear that everything is well defined. So we have to be careful, and then of course the game tree by itself is sufficient for that purpose. Is that okay? Okay. The second one have to be clear, that is how you define strategy and action. Yeah, I think I upload the slides, this slide, but I didn't upload the new one on the web, but later I'll upload it. How we define action and strategy, because last time people asked me how we define. And strategy here is you have to, in player one, it's just left and right, but player two will be depending on seeing head, what we're going to do, tail is going to do, right? So just to remind you how you write, that one I'll upload the one that after the class is you would have to be in writing this, right? Strategy of player one, right, is either head or tail, right? So that means that as the strategy space is just these two, okay? And strategy of player two, right? You have to tell me, right? Strategy two is a function of what S1 is doing, right? You can write in this form, right? Which said S2 is you will be doing this, right? If S1 is head, if S1 is tail, you will tell me whether you're head or tail here, right? So it's 2 by 2, right? So that's why usually you don't write in this form, right? You would rather write it as head and tail times head and tail, right? This means if player one choose head, what are you going to do, right? If player one choose tail, what are you going to do, right? Just this one refer to this guy, this one with this guy, right? So this is a defined strategy for player one and player two, right? And we define equilibrium, okay? It's in the sense of strategy, okay? Like what we define, okay? And you have to be careful of this is equilibrium, and we have equilibrium outcome, which is depend on what people choose is equilibrium outcome will be the strategy, the history of actions. Okay, that is equilibrium outcome. Okay, and there is also the last term is also equilibrium payoff. Okay, so let me repeat here. First one, there's a 3 level of description. Of the first one is what is strategy, and we call equilibrium strategy, right? Or equilibrium profile, right? Usually you don't write that, but that means that is described here, right? And it can be, say, S1 is head, right? And S2 is just like, say, head. Okay, choose head on both sides. Okay, and we also have the outcome. Okay, maybe we do. Actually, we don't need to say equilibrium. The strategy. This is outcome, right? Outcome in this case is just under this. You choose head, and the other one choose head, right? So outcome will be head. This is the profile induce this outcome. Okay, it's basically is the branch that actually, if this head, then this is the branch, this is the outcome. Okay, and the payoff, you can say it's -1, 1. Okay, and the reason why you have 3 types of description is because of the fact that sometimes you want to describe your result at a strategy level or outcome level or payoff level, right? It's because of you want to, because you can have if you have only one equilibrium in your game, then 3 of the description will be same. But it is possible that you have multiple equilibrium, okay, in this case, but turn out the outcome can be the same, right? Because the only different in this guy, right? Because if you have an pair 2, choose this instead, HT, right? And in that case, the outcome is still H and H, right? So that means that you have to be very careful when you. Then this is if I know not this game, but if these 2 are equilibrium, but this is still the unique outcome you forgot, right? And you can see payoff, the same idea, right? The strategy profile can be different, many more than one, outcome more than one, but payoff can be unique. Okay, so that would be the key, right? And of course, you can imagine that if people use mixed strategy, right? You may have the strategy, right? Will be mixing, say, head or tail, right? And the outcome and the payoff, right? The outcome here, when you have mixed strategy, then you will be a randomized over thing, right? And the payoff will be randomized over payoff, will become expected payoff. Okay. And I don't want to go too back. And the other thing, just how to solve this game, is by backward induction, okay, or what we call subgame perfection. What does that mean in the game tree here? It means you go, because it's here everyone make decision one by one. So that means that you can go to the very last game and see whether they're doing right or wrong. Okay, and and probably you would ask, what's different between Nash equilibrium and subgame perfect Nash equilibrium in this context? So let me modify the game a little bit, and then you will see what you're going to check. Okay, suppose this is not here, and there's some game go on, right? Suppose this is incumbent and decide, I don't know, A and B, right? Maybe I forget it, right? Suppose this is the case. Okay, I just modify the game. Okay, so maybe this chose this one. Okay, so forget about the payoff, it's not important anyway. So what's different between subgame perfect equilibrium and Nash equilibrium in the game tree context? Because some of you asked me last time, so I think about that when I take the train to school. Okay, and how do you see this is, if you talk about Nash equilibrium, okay, the only thing you need to worry, say, is deviation from one agent to another strategy. Okay, so that means that you only need to, because answer is here. Okay, you only need to care about he deviate to other strategy, right? So given this, you only check this. Is it going to be better than this one, right? For entry. And from incumbent, you need to deviate to other strategy, right? So you can choose the other strategy. Okay, but you don't need to worry about this one, right? Because choosing this has no consequence. Only need to check this one. So what we call is next equilibrium. Only need to check what about or along the outcome path or equilibrium path. So this checking along the equilibrium path, only check this one. But when you cover subgame perfect, this one did not arise along this path, but you need to check as well. So that's the subgame perfection is you need to check more than the equilibrium or the proposed path. So that's the difference. So you need to check for every single. That's why you need backward induction. You need to check out every single note that is going to make your right decision. Is that clear? So that's the difference. And that actually means that there's no suboptimal choice when people are asked to play right here. Okay, so that is the meaning. But I'm not. I hope this is clear because this is you use it when you do repeated game. That's how distinguish the two things. Okay. I think it's clear how you do this game. Okay, and simultaneous move game means player instead of doing sequentially and more than one player can move at the same time. Okay, and the example of this is like this. Okay, and here we focus on the case where player 2 doesn't know player 1 what have been chosen. Okay. So this is kind of game. Okay. And I'm not going to go to the details of that. Okay. So focus on the repeated game. Okay. And I guess I hope I convince you that if players are patient, no matter how patient they are, if they repeat this game finite number of times, you will always have defect. Okay. So the general theorem is the following: if the game only have one equilibrium, no matter how many times you repeat, it is still the same outcome. Okay, so in some sense it does have meaning about why we analyze the static game, right? Although sometimes we interact over time, but it essentially said if you repeat this many times, no matter how large it is, if people think far away enough to backward induction, okay, then you cannot sustain collaboration, right? But of course, you do remind yourself this is go against the scientific game we have, right? Where the scientific game? Yeah. Where's that? Suddenly disappear. Where? Yeah, the scientific game here, right? It's a finite game. Use backward induction, and we know that this is not the outcome that we would expect. Okay, and probably you also I want to mention, right? This is also some experiment. You may imagine that some experiment actually did this personal dynamic, right? So you ask the two agents and they repeat play finite number of times, right? 20 times or 10 times or 30 times. Okay, and then do we expect every time they defect, right? Of course, it's easy to see if they just pay once. Always DD is the thing you expect. And it turns out, I mean, if you do human interaction, indeed, they actually collaborate for some period of time. usually say, suppose the gate, I remember it's like the result is like, if they have 20 period, they're able to say collaborate within 10 to 15 period. The last 5 period, people tend to be nasty, but way before is a little bit further away, people would think they can collaborate. And you may ask why. One of the reasons I can think of is that is evolution, right? Those people who are selfish actually gone out of the history, they die, right? But some people who collaborate actually can survive, okay? And if you want to explore this more, probably you can check out some evolutionary game theory, and they can model this kind of concept. And people are hardwired to do some strategy, right? Here is, we assume people choose strategy, right? But you can imagine that people, some type of agent, and if the strategy is successful, they replicate themselves, right? And that is also a hot topic to the recent 10 to 20 years. Okay, so still an interesting thing, you can check it out. And this is the one of the most, famous strategy we call trigger strategy, okay, which essentially said we collaborate as long as we have collaboration before, otherwise we will go to the punishment, okay? And the punishment is the Nash equilibrium. So there's sometime in the literature, this is called Nash reversion. You revert to go back, return to Nash whenever there's not collaborate, okay? And you need to check whether it's Nash equilibrium and subgame perfect. So I want to illustrate again what is Nash and subgame perfect difference, okay? For Nash equilibrium, I think it's easier to see from this strategy, okay? So remember, you check Nash equilibrium, you only need to compare along the outcome path, okay? If every player plays CC, okay, this is strategy, right? So what is the outcome path we expect to be, right? It's always the history you got is always start from CC, right? So the number we will start with 0 history, nothing has been chosen, and after history 1 is CC. This is one of the possible outcome, and after second period maybe CC, right, and so on and so forth. Okay, so the situation to check is at the beginning, okay, given the other agent choose this strategy, what strategy you're going to choose? What's the most beneficiary you can do? If other people choose C, suppose you're player 1, okay, you can do whatever in the first round, which is deviate, right? And regardless of what you do in the second round, you always have only the best thing you got is D, right? Nothing more than D. Is that clear? Right? Because the other guy will always choose D, right? So if you choose C, then you got 0, right? So that means that you are comparing the payoff of having 5 in the first period, 1 for the subsequent period, right? Because the other guy is using trigger, right? You trigger him or her, right? So that's why, in order to support this outcome, that's what you are comparing, right? You're comparing along, if we don't deviate, this is a payoff, right? 4 forever, right? And this is the best thing you can do, right? Because given the other people choosing trigger strategy, okay, under this outcome, under all this history, the same thing, because what have been passed is passed, right? So starting from here, the same thing happened. So maybe I just show you here, if this is the case, this is what happened, right? If under the CC, what happened? Let me write down, okay? I should have the slide that is written here, but I just forget to upload. You don't need to copy because it will be there when I upload the slide. So in that case, if we start with CC, okay, maybe I have. So you start with empty. The thing is you have 5, right? And then, sorry, if you want no deviate, so you have 4 and 4 delta and 4 delta square, so on and so forth. All right. You want to deviate, you get 5 at one period of time, and then you get 1 forever. Right? That is what we have, right? So that's why we have this. And you can solve it out. This is coming from the null history. Okay. If the history is like CC, okay, if meaning that you deviate, okay, the first one you choose is collaborate, and then you do something else, right? That is the history you can induce, right? This is the set of history you can induce, right? Because this means that everything is C, right? And here is after this is D. So that means that you still want to compare is the following: C delta, okay. First one you collaborate, okay. Then the second one you are being nasty, but if you're nasty, then you got punished forever, right? So in that case, why this is same as the before? Because this one cancel out, right? And you divide delta from both sides, so that's the same thing. Okay, so that's why we only need to check one inequality here, right? Because if you being good, you pretend to be good guy and then bad forever, the same thing. No matter how many terms you pretend to be good guy, the same thing happen. So that's why I will have to update the slide later. But I mean, you can take a picture. That's fine. So, but that means that you only need to check one outcome, because all possible strategy you can do the same. Is that okay? Is that clear? I mean, when you first time learn it, you will just basically see this. Then you don't actually see there are actually many equations you actually the same thing. So that's why you don't need to check. Okay. Is that clear? So just to repeat, is check the Nash equilibrium is assuming the other guy is doing the trigger strategy. Okay. So you're talking about you are being the bad guy in the first round, second one, third one, fourth one, all the same. Okay. Now, and I want to say how you can check the subgame perfect is to check all possible history. Okay. Means that all node you have to decide. And the history according to this game is either C or D, right? And you may also check other than CD, okay? Other than this, okay? And you don't need to check all the path along this because we checked it in the Nash equilibrium, right? So you only check other than this, okay? But in all the game other than CC, according to the trigger strategy, okay? Everyone, the Nash equilibrium DD, right? So they are playing Nash equilibrium along the off equilibrium path. So that is Nash equilibrium. Because they're playing already Nash equilibrium, so don't need to check anymore. Right? As long as they're playing Nash equilibrium, right, in each point of time, then must be subgame perfect. Is that clear? Okay. Now we are going to define this thing formally. Okay, I think I talked about this last time at the very end is if you change this game to allow some outcome that is better, okay? In this game, you have two Nash equilibrium in the stage game. Static game, B.B. is a Nash equilibrium. D.D. is also a Nash equilibrium, okay? And what this game tries to show is, even you repeat this game twice, only twice, okay? You have a good Nash equilibrium and bad Nash equilibrium. You can support outcome that is Pareto efficient, but not Nash equilibrium, right? 4-4 is not a Nash equilibrium. People tend to deviate. But if you're able to have a good outcome and good and bad equilibrium, you can support this guy. Okay. How is we like the trigger strategy? Okay, is we do the CC first. Okay, If it has been CC, we go to here. If not CC, you go to here. Okay. And if people are patient enough, okay, getting 3 and 4 is better than getting 5 and 1. Right. So if you're good, you continue, you get 4 plus 3 times delta. If you are nasty, then you get this one, right? As long as delta is big enough, you will see the first one bigger than the second one, right? So that means that this idea of like carrot and stick, right? If you do good thing, you got a carrot. Otherwise, you got a stick. And in this case, you can support, right? Good outcome, right? It's by reward and punishment, okay? So it's actually fit what we think, right? Because, right? And if you ever have a kid, then you will see, right? In order to make the kid study, right? It's usually not the next equilibrium, right? But if you're able to reward and or punish, then you're able to do it. Okay, but it must be the punishment you're willing to impose, right? Your punishment you're not willing to impose, you cannot sustain. Okay. Anyway, so let's quickly go to the formal definition of repeated game. Okay, so because repeated game is a very special form of the game, so actually it's the description is very simple. Okay, basically here is we have N, T, and AU, right? So difference is have T here, right? Because without T, it's very close to the normal form game, except this is A but not S. Okay, this action set. Okay, it's the action that you do it every single point of time. So this is called A instead of S because the strategy is much more complicated, right? Because the strategy is like what you do in each single round, given the history, right? But the action is just simply each stage what you're doing to do, and there's a number of rounds with from 0 up to T, and you start for the game it's very normal. You start the time from 0, okay, and later you will see why it's the case because you can write your discount function easier. Okay, later you will see why we start from. I mean, there's no need to start from 0. You can start from 1, but notational wise it's easier. Okay, and less than infinity is finite repeated, and infinity is repeated game. So I think it's nothing difficult here. So history is all the action have been taken in the past, and your strategy, okay, what sometimes we call behavioral strategy, is at this point of time, depend on what history, what are you going to do, okay? And a strategy is for all period of time, okay, because this is just period T, and the strategy is for all period of time. So what are you going to do? And strategy profile is this every player strategy, okay? And as I probably is no one would define this way because this is just the definition, and the only thing you need to see is remember is the strategy depends on all the history, right? This is the formality here, how we define strategy, right? Because depend on your choice, depend on what has been happening. So it's a very complex object, right? And here we call the path generated, okay? Okay, and this is somewhat this alternative idea, right? The path along this equilibrium path, and the payoff will be just from summation of all the payoff. So that's why you can see from 0, that's the equation that is easier. Otherwise, with T minus 1. So that's why they start from 0. It's because of this idea, right? Because the first round you don't want to discount. Is that clear? Why start from 0? Because this is just notational convenient. And where am I? Okay. So it's very simple. Next equilibrium just trying to check whether the path induced by this strategy, right? And then you change to the other one, it's going to be cannot be better off, right? So I think we know it very well already. So subgame perfect, okay, is the difference is at any history, okay, Okay, given all the history, is it going to be benefit to deviate, right? The subcam perfect is every point of time, right? And do note that this history need not be induced by sigma. So it's all possible history. Okay. So even this is the path unrelated, right? That means same as what we talk about precedent dilemma. We have to check whether people in the punishment, which not supposed to appear in equilibrium, they still willing to carry out the punishment. Okay, later you will see how we define those. Okay. So although luckily is even though there's infinite game, okay, and we cannot have backward induction, so have to be very careful. Is backward induction doesn't apply because there's no finite the end we can backward induce. Okay, the question is how can we solve this problem? And in basically you can check the textbook, but in the game that mostly we care, okay, in the finite players, I think the finite number of strategy, okay, and you only need to check is what we call one-step deviation. Okay, is need to check at every possible history whether player can deviate from a strategy for one period. You don't need to think about a complex deviation plan. What do you mean by that? Is because of action, your strategy is a multi-period, actually infinite period action, right? You don't need to check if you don't need to check the deviation that is a sequence of deviation, but only this period whether you want to deviate. Change from that, and that's it. So you reduce the checking of deviation a lot, because what I mean is the following, right? It's because your action, this one, okay, you can think about, say, if I propose a trigger strategy, say for example the trigger strategy, right? Suppose this one, okay. I only need to check if I want to change my strategy of the third period. That's it. Or fourth period or fifth period is fine. I don't need to worry whether I deviate only the first, third, and fifth. What will happen? No. You just only check the deviation, only check only one period deviation. That's it. So you can see this, the check is much simple, right? Otherwise, it's hopeless to solve this kind of game. Okay. And this one period deviation principle actually applies to, I think, all the game actually arise in your maybe I should have put down the restriction, technical restriction, but unless you're doing some ways crazy game, usually does you will, right? If you find a number of player, I think if the strategy is a close and compact, I mean, that usually arise in your application anyway. So, and that should not be an issue. Okay, you can use this one. So far, I didn't see any actual applied paper actually cannot apply this thing. So it shouldn't be an issue there. So I think this is something we have already. If a game has a unique Nash equilibrium and you repeat, no matter how many times you repeat it, as long as finite, this repeated game always have this Nash equilibrium forever. Okay, for the whole period of game. And we have shown you that if there's more than one Nash equilibrium, then you can support any outcome, which I have shown. Okay. So in some sense, is the back impression of precedent dilemma is not, is say there's two diverse point of view, right? If you think our world is repeating a precedent dilemma and our life is finite, then actually it's a very dismal, it's very disappointing outcome, right? Because you always repeat the destructive outcome, right? But if you think the life is more complex, right? and actually you can support some good outcome. Okay? So whether you are optimistic or pessimistic depends on whether you think the life is have more opportunity than otherwise, right? So, and that in some sense means how you, if you look at the finite repeated game, it depends really much on how you make the model. Whether you make the interaction more complex, actually can allow the game change from one way to the other. And indeed, there's some paper actually do this. By changing the game a little bit, they change the game from the bad outcome to the good outcome. And some people write paper on those. And this is something that even this is a look at some interesting outcome, and people can tell by switch and off some button. Okay, some feature of the model actually can change from to the other. Okay, this is one interesting observation. Okay, and that is what we call the famous Fogg theorem. Okay, and I would say this theorem is one of the main research question in game theory on with the games. Is, let me tell you what it is why it's called Fogg theorem, because this theorem is everybody knows it and no one ever written down the proof for it, so that's why Fogg, and eventually someone write a theorem for them. So the theorem is the following. So to make simple, we just focus on this utility function, right? This can't pay off. What it said is, okay, if in each stage game, okay, this is A star is a Nash equilibrium, okay, and if there any outcome, okay, that Pareto dominates, that means improve everyone's payoff, okay, it need not be Nash equilibrium, okay, any outcome is fine, and we can, okay, make this happen as a subgame perfect equilibrium by using a trigger strategy. Okay, and if the players are patient enough, this will be a subgame perfect Nash equilibrium. The idea is, whatever outcome you want to support, okay, you will say we do this outcome if this is not done in the last period, we go to A star. Okay, and if you're patient enough, you can support it. Is that clear? So just same as the percent dynamic, right? CC is a good outcome. It's not Nash equilibrium. Okay, and we know DD. Okay, DD is the outcome that is Nash equilibrium, and we claim everything more than DD is yes. Okay, so maybe to convince you what do I mean by that is the following. Okay, so we have maybe I draw the whiteboard. So let me draw this in this diagram. Probably will allow you to see. Okay, so what I'm going to draw is the utility of player 1 and player 2 in this diagram. Okay, and here I have 5 and 5. Okay, and I have 4 and 4 here. Okay, and this is 1 and 1. Okay, so what are possible payoff in this diagram? Okay, so 4-4 is a feasible outcome. Okay, and 0-5 is a feasible outcome, and 5-0 is feasible, and 1-1 also feasible. Okay, so if you allow mixed strategy, right, this is the set of possible outcome. Okay. What it's trying to say is dash line is not including, right? So any payoff in this red zone can be support as outcome perfect equilibrium. Okay. So anything here. The reason is maybe some mixed strategy. Okay. But anyway, if here or here, if this is followed, then you go back to here. Okay. So that is the main idea of the okay. Of course, we don't talk about mixed strategy, but in case we add an outcome, okay, we don't talk about mixed strategy here, but I mean it's possible to do that. But let's focus on the easiest case. So suppose I have the game of C, D, C, D, right, which is 4, 4, 5, 0, 0, 5, and 1, 1, right? So suppose I have another outcome called E, right? Suppose we have, say, 4.5, 3.5. I don't know, randomly put any number there. As long as this number, okay, in here, this thing can be support. How do we do that? It's just like if this is not the case, we go back to here. Okay, as long as we make this kind of payoff, still make this Nash equilibrium. Okay, maybe we just keep this 0, 0. Okay, no matter we put any number here and number here, right? As long as within this zone, this is fine. Okay. The idea is if they are not, if they deviate, I go to 1. I go to 1, 1. Okay. And if you're patient enough, then this will be support. Right. So easy to check how you can support it. Right. The proof is very elementary. Right. Support this outcome, you have this payoff more than the 1, 1 forever. Right. And 1, 1, because it's Nash equilibrium, it can be sustained by itself. Right. So that is how why this is called Fock theorem, because everyone knows it and no one actually proved it. Okay. Is that okay? So sometimes you may say this theorem is boring, right? Because anything can be support. So what's the prediction here? Right? You say, okay, oh no, okay, now we know the worst outcome is there, and then anything better than worse can be done. Can we say more? Right? I mean, you are saying, okay, this is good, this is good, this is good, this is good. Okay. Can we say more than that? Okay. And in this context, usually you would focus on the Pareto frontier, because you would think if they can repeat, I mean, you would focus on the Pareto efficient, right? So that means that if you try to apply this in practice, you will focus on the frontier. And the problem is which one you want to pick, okay? And actually, no, in the repeated game literature, as far as I understand, no one actually tried to pick any equilibrium. They will give you the whole set. And probably you want to ask what would likely to be the outcome. You probably think about what we call bargaining model. You would propose depend on how things arise, then everything is possible here. Okay, so we don't go to, in economics, we don't go to detail which one's outcome, because it depends on what, if you want to do prediction, then you need to know more this kind of game, right? Because that's telling this prisoner dilemma or this kind of game, it's hard to predict which one is possible. You predict this all possible, and which one is more possible than the others, can depend on a lot of stuff, right? Depend on custom, depend on tradition, depend on how to agent characteristics, so on and so forth, right? So economics is, I think, given this situation, you can't tell too much. Okay, and it's possible this is the best outcome. If you think the two guys are equally good, the symmetric one is the one that you would predict, right? So you would, if you impose the symmetry assumption, you have a unique outcome for 4, right? If you don't, then you would be somewhere else. Okay. And maybe I just go a little bit about this because I think we start late. So let me finish this example. I think it's very important. Otherwise, it'll be good. Okay. So this is a model of a cartel. Okay. It's a model that how two firms can collude. Okay. Okay. And then we focus on the case where all the action is observable. Okay. So that makes the collusion easy. Okay. In a case that action is not perfectly observed with some noise, okay, then collusion can be harder. Okay. If you notice, like, right, if the wife know what the husband is doing every single moment, it's very difficult for the husband to have affairs, right? So that's why there's a tracking app you can install in your husband's your boyfriend's phone, right? They keep track of him, then no way he can do bad thing, right? Same for the man, right? So now how can we look at this problem? So same standard, we define the quantity, define the market, right? That's how you, if you write the game, that's how you write, right? Start with the market quantity and start the price. So this is the seller, this is the firm, right? So this is how usually you write the paper, right? You start with describe the environment and then go to the agent, right? Agent, the cost, and okay, I basically skip how to solve this problem. Probably you would know how to solve this game if two firm cannot is AC minus A minus C over 3, and the price like this. Okay, and if only single guy monopoly is AC over 2, okay, and A plus C over 2 for the price. And you can easily see that in the duopoly, which is Condorcet's equilibrium, okay, each firm produces A minus C over 3. The total production is 2/3 of A minus C, which is more than the monopoly, right? And the profit of monopoly is higher than the sum of the profit of Condor, right? The duopoly. So the two guys actually have intention to reduce the quantity to boost up the price, to boost up the joint profit. But they can't do it because if I reduce, the other guy want to increase, right? Because if you recall, the best response, maybe I can erase this one, right? So if you still remember, this is the game, Q1, Q2, this is A minus C, this is A minus C here, and I use different color. This. Right, so that's why this is the best response, Q1, and that's why Q2 not producing this year. Why this is monopoly, and right, and we know this is AC over 3. This is the Nash equilibrium. This is duopoly outcome. And this is monopoly outcome. You can say this or this, right? So what actually they want to collude, if they want to symmetric collude, they want to go to this outcome, right? Because this is the best outcome you can get, right? So what they can want to do is to go to this, go to here, AC over 4, AC over 4. So they want to go to this guy, right? Because AC over 4 is, sum of the AC over 4 is just the monopoly, right? So we want to go to here. But you can see here is not Nash equilibrium, right? Because if player 1 choose A minus C over 2, player 2 want to produce this much, right? If player 1 keep here, player 2 want. If player 1 is going to choose this one, player 2 going to choose this guy. If player 2 choose this one, player 1 will choose here, right? So neither, this is not on the best response of anyone, right? So anyone choosing this, the other guy want to enlarge production, right? That's what happened actually to OPEC, right? OPEC is the biggest cartel, open cartel. And why it can exist? Because the government cartel, right? There's no world organization to handle the cartel between country, right? But within country, we cannot do cartel, but across country you can cartel. But even OPEC actually fails because every firm, if often is once the OPEC have a meeting, they decide to cut back their production. One country say, okay, I produce more. Usually Russia, right? But sometimes sometimes Iran, sometimes Iraq, but OPEC tend to produce a lot. Okay? And sometimes USA, because USA is not belong to the OPEC. So that is you sometimes Saudi Arabia, they just, okay, I don't care, I just pump. Okay. One of the reasons why Saudi Arabia can keep pumping is because their production cost is very low. Basically, cost is less than $1 compared to other places more than $30 or $40. So we can always pump, there's no cost. To him, it's like free thing, just pump. Okay. Anyway, so that is the graph here. So how do we support this using our sugar strategy? The way to proceed is, okay, each firm produce AC over 4, okay, and if any firm deviate, we'll go to cannot forever, okay. So we're in heaven. If not heaven, then hell forever. Okay, so that is the trigger strategy. So first, how can we support this? Okay, we have to figure out what's the discount function, right? Because from the fourth theorem, we know this is possible. There's no need to do anything, right? Because you go back to Nash, right? So the only thing we need to check in this one is to figure out what is the discount factor you can support it. Okay. And first, you calculate under this outcome, what's the payoff, right? So it's the payoff along the equilibrium path. Okay. If everyone is following this strategy, then they earn half of their monopoly profit because they act as if monopoly, right? So this is half is like this outcome. I think this algebra, I don't need to go one by one. I think it's okay. Okay. And the next is look at the profit under punishment, which is Nash equilibrium, which is A minus over 9, which is this one. Okay, so you can think of this is actually the prisoner dilemma here, CC. Sorry. Hi. Is it working? Whatever. So the CC. This is C and D, right? So you can imagine this prisoner dilemma game. This is, you collaborate. So you got what we have is a minus c over x square, right? Maybe I write. Can you see? Okay. If you deviate, you become a bad guy. So this Nash equilibrium is a minus c over 9, right? Same for the other guy. So what is left is you need to figure out what is this outcome, right? Because actually in this trigger strategy, you only need to see whether collaborates this one. This one is punishment. You need to see what is the next key thing you do, what is the gain. Okay. And here is very simple, right? You say the other guy is still very naive, right? You see how you can gain from that, right? And you only gain one period. So you choose this outcome, okay? And the deviation, what you gain, okay, is figure out what is the maximum of this. And you solve it, which is 3 times, is you calculate this. I think you can handle the algebra like this. Okay, you don't need to worry about this guy. Okay. So then how can you check whether this is a subgame perfect equilibrium, right? Same as how you do the present dilemma, right? So under cooperation, you have a minus c square over x forever. If you deviate, you would get one period of this gain and this forever, right? So we just need to check this bigger than this, right? As you're done. You don't need to check whether you deviate otherwise because this already a Nash equilibrium. I'm going to check this one. Checking one is already checking everything. Okay. Actually, we have to check, but because of this kind of game, is you can skip all other check, right? Because you don't need to check for every period deviate, the same thing, right? Because trigger strategy. You don't need to check whether the deviation along the punishment, do they follow punishment? You don't need to check because Nash equilibrium already. So you only need to check one deviation and you actually check all the deviation. Is that clear? Okay, have to be very careful because the book basically usually they say, okay, check this and done. But indeed, it's not checking only one. You check one, check all the thing. Okay. Is that clear? You may have to check all the subgame, but in this particular situation, you don't need to check. Okay. And I'm not going to bother with the math. Okay. But this is just very simple algebra. You can easily check delta greater than some number. Okay. I think you guys have very good math. You don't have to worry about that. And the main message going to show is, okay, as long as you're patient enough, you can support this outcome. Is that okay? This is very simple. It's nothing new. Okay, this is easier thing. You can, you know, if you learn master or game, you learn introductory game 3 class, this you learn, right? So what we're going to tell you now is what happens if lower than this one. Okay, what happens if you're below 9 over 17? Okay, so now what we have is this. Your discount factor from 0 to 1, 9 over 17, you know, you will have a outcome that everyone can conclude. Okay, the question would be, what happened to here? Okay, this is Fock theorem. Yeah, Fock solved the problem. What happened to here? So what you guess? What's your guess? The thing is, this will show now is this outcome you can't support. You cannot go to here. You have to go to a little bit earlier, somewhere before it. Why? How can you think about this way? Why is the case? Think carefully here. If delta is 0, what do you expect? If delta is 0, what do you expect? What's the outcome? Sorry? Yeah, DD, right? So if you delta is 0, it's here. And here is the outcome where delta is bigger than 9/17. So if you get lower delta, you increasingly along this line. Is that clear? The reason is being that if you are not so patient, right? That means that this gain is large, right? Because so what you're going to do intuitively is to reduce this gap that can support, right? Because you try to make the gain from being selfish is less, right? Because remember how you compare, how you do the deviation, right? You look at this gain compared to this plus this, right? So how can you support this thing? Is to make sure that this guy is little, right? More the reduce this one, then you can support. So that's the idea here. Okay, so we look at the math. Okay, so this is how we different from the master level, right? The master class in the introductory game theory tell you this. Okay, now we tell you how to characterize this guy, and it's very natural, right? So we go back, depend on discount factor from 0 up to that point. I hope this is something new here. Let me quickly. Okay. So is that okay? So the first thing to do is, okay, we need to figure out what you can support. Okay, this will be depend on delta. Okay, this is the outcome that depend on delta, and the punishment is the same. DD is the same. Okay, so this one will be depend on delta, and of course this one depend on delta as well. Okay, and so we figure out that, okay, if under the collaboration, if everyone produce QC, you also produce this guy, right? You just if other guy remain the same, what is the best you can do, right? So this, let me write down here. So so it's like CC, CD, okay? There's no change about DD, which is A minus C over 4. Oh, 9. 9 squared. 9. So what is this? Is A minus A is AC, QC minus C over over just A minus QC minus C. QC, okay, it's your payoff. If you deviate, your payoff is this one. A minus QC minus C over 4 square. Okay. So that is simple. You compare payoff, paying this one compared to deviation of this plus this. Right. So basically, look at this forever. And if you deviate, you get this plus this forever. Is that okay? So this is the payoff being collaborate, right? This is the payoff. You pay this forever, or you deviate, you get this one, and you get this forever. So look at the. So you want forever collaboration better than you deviate, and you get this forever. Okay, and as we can check, I mean, there's some algebra. I'm not going to go to the detail, but this graph is like this. Okay, so turn out to be this expression. Okay, so what this expression tell us? Okay, this expression is decreasing in delta as we would expect, right? The higher the delta, okay, maybe I have a diagram to show what is this graph looks like. So it's good to have this one. So this is delta and this QC. Okay, and what you expect? If delta go to 0, you mentioned, right? We will have the outcome of Nash equilibrium, right? Which is QE. And here, which is, look at the graph, is just AC over 3, right? So look at the delta is 0, 0, 0, right? It's 1 over 4. Delta is 0, right? This guy, right? And we know if delta is more than 9 over 17, okay? It's close to 9 over 17. It will go to A over 2 minus 4. So it's just like this is the half of QM, which is A over 0.4. Like this. Okay. I don't know. It's like this concave or convex. I don't know, but I think this is the graph. Looks like, right? So this is a complete description of this game. Okay. Is that okay? I mean, I forgot the concave or convex. I should have checked it. I add back the graph when I update the slide. Okay. So this is a complete description, right? So depend on how patient people are, right? If they enough patient, they can collude. If not so patient, they can only collude at the level that is not so efficient, right? So in some sense, what we are saying is the how collaboration can be done depends on how patient we are, right? If why we see sometimes the outcome is there's a Pareto inefficient, it's not because we can't exploit the opportunity there, but rather people are not so patient, and that's why we can support a low level collaboration, because to support that one, that means we need a lot of patience. If not, then we can't, right? And that's why we see so many inefficient things happen in the real world, right? Not because of people are stupid, but because of their huge gain in being selfish. So that's why we can only support this level of collaboration. Okay, and I think that's a very good to explain Pareto inefficient. Okay, I mean, you will see efficient outcome as a normal, but this tells you the Pareto frontier you can achieve can be less than what we can imagine. Okay, so let's have a break. Sorry for taking too long for this first section. Have a break of 10 minutes, and then we can come back. Yes, I will let's have a break of 10 minutes. I go around to check if you have any question. Sorry for just a long section. CD 血压里面的那个，就其中一个人奥德卡，他给，比如说他从100的10这样的话，那么他对，
说我减少了的一个就是改变我的就 commit to burn，然后就可以做成这个效果。比如说我去介绍说，我要做坏事的话，我做的不好的事情我就去赔偿，那么就可以什么就是有办法可以有办法，其实法律的一个危险，为什么 sign contract，right sign contract 之后改变这个配偶，就是 third party 来改变的。这点是三等分别，这真的是三等分别。哦，是有很多，就是这个但是可以给他三等分别，因为做怎么画了，它不能画三等更小的层面。这有一个数学问题。可以好，给他的下一个会。在发表是他们说，怎么会我追求这一层，我说这一层。在我这个，在我和这个广告的任何人，到底都很差，小孩子是吧？他说以前没有人换的这个就是 A 的具体科的来好的话，我还想说，好条件上我觉得可能不三全面。对，正常。哦，是漏了对吧？哦，对对对。I find this fascinating. Because usually the book tells okay more than it tells about less than because that is in general when you in case of they look almost all the case over especially when probably and probably one person those things like people how people take it over. But when the game by the next doctor probably over the time, then you don't have this professor as we underline that's the game to have take over. So basically all the action so that is what they can occur. information set, and it's still looking like, I mean, it's first information to see. So when they decide, so this kind of is very, it's very important. In this kind of company, the perfect partner, you know what action is program. So your history is that of the action. Sometimes you pay that monitor. You can't fully monitor. Then the history of that of the say suppose in the case the data report. You here are the point that you exactly know the point of other, but you overlap actually sometimes good point is the time. So this provide on the overlap. I can see exactly which type of you see every point, right? So you have and the collaboration is part of the model. You want so we have to punish. Sometimes you can punish. Sometimes go back. So punish for and sometimes punish, sometimes you punish something that they are not supposed to. So they are possible. Sometimes punish you don't have to punish. Sometimes forgive some debtors. So that's all. You put around you have some stuff. You can see everything. Punish and you only punish sometimes. Last means sometimes. That is right. That's why you see the guy that is a year for 1 day or sometimes, and you will punish the people sometimes. So punish some of the other stuff. So you punish like punish the guy, sometimes you expect. And thing, there will be some things like somewhat sometimes what style you try to stop going on in the I did my post match the
Hi. So I hope you can see this is a very interesting graph. Okay, and this is I like it very much because this shows you how collaboration depends on how people are patient, right? Because people are short-sighted, right? Then they become not so good, right? So there's a worse outcome you can get, and people get more patience, then actually things become nicer. Okay, and there's a reason why in the marriage contract, right? When people get married, there's no time limit to that. Okay, I mean there's some country that put time limit to the marriage, but in most of the marriage contract between man and woman is a infinite horizon, right? Infinite horizon in that contract doesn't mean that is infinite life. Okay, the idea is you can think of the mentality is everyone would think the future will continue with delta probability. Okay, delta, because the payoff like this, right? You payoff is like 4 plus 4 delta plus 4 delta square, something like this, right? That's what we do. You can imagine that delta part of the delta is you think the future or the relationship will continue with delta, right? Of U1 is like P delta, right? P probability, you can continue, right? So that means that you can imagine that a continuing contract, a contract without endpoint, is a infinite game. Okay, it's saying that okay, we keep collaborate. Of course, there's an external force that make this thing doesn't happen. Okay, and that if you think the future P is very small, right? Continuation is very small, then people will be very selfish, right? If the future is still there, it's very far away from our imagination, that you can sustain a collaborative outcome. Okay, so actually that's what happened. Look at the US president, right? He is the first guy in the executive branch. Okay, and he has superpower. He can do whatever he likes. In particular, he can pardon anyone. What does that mean? It means that he can write a line in a document saying this guy will be exempt from particular criminal investigation. Okay, so someone is being sued and he can write a line, say, okay, he is not guilty. Okay, he can do whatever he likes. Okay, but of course, he usually would not pardon murder or those kind of crazy things. Usually a civil liability. But you will see people, when the president go into office, he usually don't do anything at the beginning, first few years. But at the very last 2 weeks of his office, he will sign like crazy, keep signing a lot of this pardon document. And at the end, at the last day, he will sign humongous papers, pardon this and that. Who is going to pardon is those who give money, campaign contribution. Okay. At the very last day, he do all the perks, he do all the thing, right? Because there's no more future, right? Because his last day of being the in this job, right? And then he tried to grab whatever at the end, right? So that's the meaning, right? I think that is one famous quotation from the Chinese officials. What they said is, use your rights when you have. Once expire, it no longer valid. 有权不用，过期无效. So that is what they said, right? So that's exactly what it means. Is when you have power, you want to do whatever you like, but because of once it's expired, you don't have anything, and you don't want to do it at the beginning because you think still the future there. But once you think the future is not there, then you just do whatever. You're just being very selfish. Okay, so that's what you observe in the situation, right? So also you can see why Nancy Pelosi, right? She went to Taiwan in the summer. Why? Because he knows he's going to get out of office, right? So that's why he tried to do whatever she thinks that is maximize her payoff, right? Because she's going to say, okay, I'm not going to be the speaker. So yeah, do whatever I think right now. So everyone like this, right? At the very last period of the term, he or she want to do whatever that is beneficial to him or her, right? So last, this one, I want to be quick here because I don't think I want to go to the math in this one. I want to give the idea because it's rather technical. Okay, so here is by what we call Pinot-Cook. So what is this whole set of slides saying is we consider game where with much richer environment. Okay, and you can check in this game only M is the Nash equilibrium. You can check because M is here. Okay, if player 2 choose M, player 1 choose M because 7 is better than 3 and 5. And if player 1 choose M, player 2 also want to choose M because 3 is better than 7 better than 3, 7 better than 5. Okay, and this is what he called a discrete Carnot. You can produce low quantity, medium, or high. Okay, both low actually is Pareto efficient, right? But if other people choose low, you want to choose high. Choose medium, right? Okay, so this is the game, and what I'm not going to do the detail, okay? But the thing is, first you want to see if this can be supported, right? You can forget about this. Basically, it's a precedent dilemma, right? You should forget about this guy. It's a precedent dilemma, right? So this is just the standard idea, right? 10 forever, you defeat 15, and then you got 7 forever. Okay, so this is the payoff. Okay, so this is nothing new. The new thing is, can we do better than 508? Okay, can we have lower delta? The answer is yes. How can we do that? I'm not going to the detail, but let's see what is the strategy to support this. Okay, so the idea in the Nash reversion, go back to Nash, is you actually punishing the player that is doing the great, right? Is regardless of who do the wrong thing, we punish everyone as a punishment. That is not efficient. So how can you improve the punishment? Is we call penal code, means that you have a punishment for each player who deviate from the bad thing. So what does that mean? Is the following. It is saying that, okay, we will go to LL forever, right? If the LL before, you pay LL. Okay, so there's no change. The only difference is punishment. You have player specific punishment. Okay, here is if player 1 deviate, okay, we'll play this guy. If player 2 deviate, we'll play this one. Okay, so instead of single punishment for both, we have punishment for each. Okay, and let's see MH and LM. What does that tell us? Okay, so if player 1 deviate, we'll go to MH and LM. Okay, we will go to, if player 1 deviate, we'll go to MH and LM. Okay, so why this is better than 7-7? The reason you can see is this and this is worse than 7, right? So if player 1 deviate, actually he will get worse outcome. And you can see player 1 also better off. Okay, actually the punishment have two purposes. One is to actually make the deviator even worse, and also reward the punishment, the one who actually player 2 who actually don't do bad thing, right? Means that along the punishment for player 1, player 2 actually is also better off. Player 2 is even worse compared to 7-7. Let me repeat again. Before, the punishment is 7-7. Okay, now we consider punishment in the way that player 1 is even worse, and player 2 is actually benefit along the path. Okay, and okay, so that's the idea. So why this is better? Okay, and I haven't finished it. Is okay, if they are good, they continue this one. If player 1 anything bad, we'll go to this one. Okay, and along this one, if player 1 deviate, we'll restart this. If player 2 deviate, we go to this one. Okay, whoever deviate, we go to one of them. Okay, you will ask what happens if two guys deviate together, but this not, we don't need to check this one, right? Because we need to check every history, only one player deviate. Okay, let me repeat because it's very important. Okay, the idea is we have player specific punishment, right? And remember before, everything is MM here. Okay, the punishment in the next version is MM, everything is MM, right? But now we have more specific, more fine-tuned punishment. Okay, is whenever any player deviate, we will start from here. Okay, and yeah, question. Yeah, but if you say, suppose you're here, right? Suppose you should pay, player is after punishment, player 2 should choose M, player 1 choose L, and you say player 1 choose M, right? But if they did it, we start. Of course, we will have the map to support this is right. I mean, have to make sure that this is correct. But how you get punishment is if you don't do this, you go to here, and here actually give you actually worse. If you try to escape, actually you can't escape, right? Here you try to escape to here, right? Actually here I will start here. That's how this is being punished. So if you don't follow the punishment, I punish you. Okay? If the one who's supposed to punish don't punish, you get punishment. Right? Because the punishment here, right? Actually tempting not to punish. Even for player, right? If player 1 deviate, right? Player will play here. If player 2 actually don't punish, we actually will punish him. Okay? So everyone have to carry out the plan like this. Of course, you will say this is very complicated. Okay? But this is trying to show you in a more complex punishment, you can able to sustain 10-10. Okay? I'm not going to detail to check, show you how to check every single thing out. Okay? And turns out, I mean, I'm not going to check. I mean, you can check by yourself. And turn out it's much less than that. It's 4/7. Okay? Before the one is 5/8. Okay? So you lower your punishment. I think by now you can check easily. I mean, with your skills. Okay? And the point is this is not very important. I mean, there's no one actually carry this out. Okay? You don't need to carry out this operation for your calculation. But this is just to illustrate there's a agent specific punishment. Okay? And that can lower the delta. Okay? And this is characterization is not important because this outcome actually turned out to be we have this result. Okay. What it means is turn out to be any min-max payoff can be supported. Okay. What do you mean by min-max payoff? Okay. Is okay. Look at what other people can do. Okay. Try to make you worse off. You can at least guarantee the payoff yourself. Okay. And any payoff level that more than this one can be supported. Okay. And is it, can you read this one? So this is saying that, okay, whatever strategy what other people do is the other guy are crazy. Okay. You try to make sure that you have the minimum payoff. Okay. And you try to defend them by choosing the what's the maximum level. Okay. So that's So basically is look at this, maybe look at this example. Okay. And what is the level? Okay. So here, if player 2 choose L, the maximum I have 7. Sorry, the minimum I have is 7. Right? And I choose the one. The minimum, the max. Okay, let me write that down. I think it's easier. So you will have first find the maximum given your strategy. Okay. Okay. So what we're going to do is to find the maximum you can get given other people's strategy. Okay. Given the other guy choose L, the maximum is 15. So let me highlight it. No, I circle it. And given the other guy choose M, the best thing I can do is 7. X given the 0. Okay. And it's 15, 7, 0. The minimum is 0. Okay. So in this case, as long as the equilibrium is going to give him more than 0, it can be support. Okay. So it's symmetric, right? So as long as the outcome give the player more than 0, okay, this outcome can be a sub-game perfect lattice equilibrium if they are patient enough. Is that clear what it's doing? Okay, just to repeat. Okay, you look at the strategy of other player, choose the maximum. Okay, and pick out the minimum of this. Okay, this is your restoration level. So this is that. If this is like the worst case scenario, you can, right? Even you are 1 versus the world, right? This is you get 0. Okay, as long what the Fock theorem in that sense is, as long as you get more than 0, this outcome can support. Is that clear? And how you support is you decide a player specific punishment as we have seen. Okay, of course the math is super complicated. Okay, but we don't need to care. Okay, that behind the penal code I have just said. Okay, everyone have a specific punishment. Okay, like punishing to this one, make sure that right some mixing get you to this one. So that's how, because you're patient enough, we're able to make sure that you would get this. Okay, basically the idea is like we make sure you get this if you are not, you're naughty. Okay, and because people are patient, they are willing to carry out this kind of punishment. This is the intuition, right? Because everyone's patient and everyone can collaborate to make you get 0. So that's why anything more than 0 can be support. Okay, so that is the idea. Is that okay? I hope that is clear. Of course, you can say this outcome is rather not very useful because Fock theorem tells you anything can be done. Okay, but of course, the more interesting case as you would want to do research is to see how this thing, how the lower, right? Because everyone knows more than delta you can support, right? I think the most interesting thing is less than delta, what you can do in your model, right? Because you can basically, everyone know the Fock theorem, right? There's nothing interesting to talk about this. This is rather interesting, right? And I think in business application, this is also very important, right? This is where CEO, right? All of them are not very patient, right? Let's end up in here rather than this guy. Okay. And I hope it's okay. although I skip all this calculation, I think with all the technique, I think it's very clear how we can derive. Okay. The reason I skip because we have more important thing to talk about. Is that okay? I mean, you can go home and check. If there are any problem, you can ask me next class. Or you can just drop me an email. I can explain to you because of the time constraint. So what I want to talk is slightly some application of game theory because with the game, because I think it's rather interesting. So I will just go, because of the time, I just go over the ideas. Okay, I'm not going to go to the math line by line. Okay, but I think this slide is already written in a way that you can check it out by yourself. Okay. I mean, unless you're really working on this problem, you don't need to worry about the math, right? So the idea is more important than the other case. Okay. So this paper is very interesting. Later you see the conclusion is funny. Okay. So we focus on the case of what we call perfect monitoring. Is you actually know what happened. The only difference on this model is the environment is stochastic. Okay. Before we have Common model. Okay. This model, the demand P is 1 minus Q or A minus Q, right? So this is I don't know, is stable every period. Okay. But now consider the demand. Okay. Is inelastic. Okay. But it's either high or low. Okay. And you can imagine this is what we call the macro model. This is a boom. This is a resection. Okay. Boom is a bust. And the probability that is boom or bust will probably 1 minus W and W. Okay. And the demand for each good is for two different firms is independent. Okay. The boom and bust is not yeah, probably not boom and bust, but more like some people like your good or not so like your good. It's like a cycle, like faction, probably like this. Okay. And people are willing to pay $1 for your good. Okay. So what is this model is delivering? Okay. Is they compete in a Bertrand world. Okay. So if you set the lower price, then you get it. Also the Q, I think, sorry, the Q is the error gauge. I think I have so yeah. So it's the two firms in the market. Okay. So you set the lowest price, then you get the whole market. If the price is same, you get similar. But the quantity, the total quantity is can fluctuate. Okay. So if you look at this history, just history of the quantity, right, and also history of the prices, right? Because this is a you can imagine this is the quantity is the one that chosen by nature, whether high or low. Okay. So the history is a little bit more complicated. Okay. The history is not just the choice by the players, but also what the nature tells you, high state or low state. Okay. And the strategy depends on history, decide whether you produce Q or L. Okay. Because at the beginning, you know it's a good economy or bad economy. Okay, let me repeat the game because probably it's not entirely clear. So at the beginning, you know the demand. I should use T here. That is the reason why it's confusing. T here, T and T prime. So each period, the demand, total demand is either L or Q, so basically boom and bust. And you at beginning of the game, you know whether it's a good economy, bad economy, and good and bad economy is have some probability, and each period is independent. Okay, and people willing to pay $1 for the good. Okay, at most. Okay, so that means that at most you can set $1. There's a boundary you can set. Okay, and so and they engage in Bertrand competition, right? So your strategy depends on what has been done and what is the economy at this moment. Okay, so this game, not going to go through the detail. Okay, but one you can actually check. One interesting point is, of course, if players are patient enough, you will always have one, right? It's not surprising, right? Because if you're patient, I mean, you can always get the good outcome, right? There's nothing new here. And if people are not patient, you get a Bertrand outcome, right? Everyone says zero price, right? This marginal cost, right? And this is the monopoly outcome, right? So what interesting is in the mediate, right? Is that clear? What is it doing here? Maybe I draw a picture. Again, it's very interesting to look at this diagram here. This is delta. Again, it's a price. At most is 1, low as 0. This is also 1 as well, right? What it essentially said is, if delta is large enough, okay, and they can collude, right? They can collude. They will charge 1, right? Because 1 is the maximum people can pay, right? And if the 1/2 is here, maybe use other color. Okay, you get here. Why? Because they are not patient enough. The group Bertrand, right? Bertrand outcome is 0, 0, right? Everyone will set a 0 price, right? So you either have monopoly outcome or Bertrand outcome, right? Of course, you can imagine if this game is there's no uncertainty, you draw a line there, right? I mean, if there's no uncertainty, you expect something like, I don't know what the shape, but there's some like what we have drawn there, right? So the interesting thing is, if there's uncertainty, okay, at the beginning, what you get is very funny. What you get is indeed, okay, the following. Turn out to be, you're able to do this when the economy is bad. And the economy is good, you can only support this one. I mean, this is QL, this is Q high. Right? This rather not so intuitive is when the economy is bad, actually turn out that you can end up in a good state of the world. Okay, you can collude. But if you are in a good state of the world, the price actually lower. Okay, and he used this model to kind of say price are counter-cyclical. Okay, high price at recession, low price at the boom. Okay, so kind of sometimes explain some macro thing, right? Because you expect usually the price are higher when the economy is good, right? Price are lower, the economy is bad. Okay, but if you don't have with the game, okay, and you can end up in this kind of outcome. So why is the case here? Same idea. You have to reduce the collaboration benefit, right? If you're bad, It's already low, so don't have to worry about it. If you are good, then you cannot be that good. If you're that good, then you deviate. Right? So the idea is to make sure that the deviation gain is not that much. Is that clear? The same intuition. There. As we done there. Why we have to increase the quantity? Because of make sure that you deviate is not so much gain. The same idea goes on. Okay? The idea is try to make sure that if you deviate, if you gain so much, then you can't. So you have to end up in the best day, don't worry. Your best day already low, right? So not much gain to deviate. But if your good stay, you have to make sure the good stay you don't actually earn that much. You have to lower the gain for the good outcome so that to sustain. Is that clear? I think this is not very good. I think I have to. This depend on delta. I think somewhere. I don't know, somewhere right there. I don't know. I mean, you can just draw it. It's not. Yeah, it's increasing. Yes. 1/2 is what? Yeah. Yeah, something like that. So, is that okay? This is symmetric. Oh, asymmetric? Yeah, you can. But this focus on the symmetric one. Well, as we see, it's fourth theorem. So many things can happen. Remember I said fourth theorem said anything on the frontier can happen. So we don't know which one to pick. Usually we focus on the symmetric one. But as you said, I mean, the asymmetric one can be very complicated. I mean, so that's why in economics we focus on symmetric equilibrium because of the. But as you're right, I mean, you can focus on asymmetric one. And the problem of asymmetric one is there are many ways to asymmetry. So usually you have to focus on some class of equilibrium. Yeah, you can say some problem. Maybe you can imagine one firm is a leader. He always go to one, right? Yeah, it's possible. It's possible to do it. But what he wants to show is the price is low and good time, right? Compared to the bad time. So that's what they want to show. And usually symmetric is sufficient. I mean, yeah, there's many equilibria. I mean, the one we saw here, right? We also, I mean, this one, right? We focus on the symmetric one. I mean, it's possible to have a symmetric one. I didn't mention it out. So because fourth theorem, I tell you many things can happen. So, but we focus on, say, in this case, you can say firm one is one output, firm two is other output. You can also do the same thing. And you can also support those. But we focus on a symmetric one. That means very good question. Is that okay? I hope I answered your question. So this is the proof. I'm not going to go about it. I think by now you should be able to see the difference. And the one important thing I said, right, is in the good state of the world, actually the price lower than the idea. And one of the reasons is because of you can collude here is because of if you deviate, okay, the future is brighter tomorrow, right? Because now you're in the best state, right? You deviate, you gain a little bit, but the future has a lot of things, right? So that's why you can collaborate at a better price, which is, as I said before, right? Repeat, you are in the recession now, okay? The gain of deviation is limited. right? Because the worst case could get everything, right? The whole market, but the demand is little, and the future has a bright future, right? So that's why you easy to collude when the world is not good. Okay, that's the idea. Okay, but this is the same as what we have said there, right? This is the model, right? To explain in the paper, explain why you have a long time of high price and some time of aggressive competition. That's why you will see a lot of the time it's a high price and end up with some price competition in the good time. Okay, so when the economy is good, right, you would have a price to compete, right? That's why you see price war only exists when the economy is good, right? In a bad time, you don't see that, right? They stop fighting. So that is the argument of the paper. Okay, and of course, if you try to see why I have this paper for you, because when you try to look at firm competing in a long run, most people cite this paper. Okay? So this is not just for the sake of macro, but people talk about competition between firms. I mean, even in business journal, management science, I saw people cite this paper. So I think it's good to mention it. Of course, this AER, but in the 20 years ago, you can still read it. It's not something difficult. You can read it. With the knowledge you learn from this class, you can read that paper. If you want, you can read it. Because the math is already there. I mean, I think I cover most of the math in this. We want to see. Okay. So lastly, we want to give some taste of what we call imperfect monitoring. Okay. And I would say this is a very huge literature. There's a book, okay, several books actually studying this kind of situation. What is it here is very similar to the model we study, Bertrand duopoly. Okay. Also, we have a good state of the best of the world. Okay. We also have demand curve. Okay. Okay. Same as what we have. Okay. Even easier. Okay. Because the only difference of this model compared to before is, okay, firm cannot observe, okay, cannot observe the state of the world. Okay. What do you mean by that? Okay. He didn't know whether if I got zero profit, okay, is it because of the world is bad or the opponent cut the price? Okay. I have zero profit. Okay. I look at every period of time, I decide my price, right? And I can only observe whether I got a profit or not, right? But I don't know whether zero profit is due to which actually recession, or it's just the other guy is a nasty, right? Is that clear setup? So before the previous one, remember, the previous one is you observe the quantity at the beginning. So you know exactly the state of the world. This is the difference. And now you don't. You don't observe that one. Okay? You don't observe that one. Okay? In the good state of the world, okay, you would get two. Good state of the world, get 2, get 0 with the best day. Oh, I think something happened, not written there. If best of the world is 0, 0, I think I The slide is gone missing. The best day you get 0. Sorry, I should have put them back. Yeah. Okay. So what is here is what you learn from the profit monitoring, the grim trigger strategy, which means that if you do bad thing, I punish you forever. It's not feasible. The reason is the other guy actually don't do any bad thing, right? Because 0 can cut due to recession, right? So if you do grim trigger, what happens is if the world is bad, you go 0 every period 0, right? Remember, trigger is when you see 0. If you go grim trigger, means if you have 0 profit, then you will just produce as you set the price to 0, right? But in that case, you cannot sustain collaboration. The reason is you have bad economy for some time, then you got 0. You will punish. You punish, then you can never able to go back, right? Because grim trigger means you punish when you see bad thing, you punish forever, right? But it's possible that nature, by some probability, you will go to bad state, right? So you cannot use this. That means that what you're going to do is a little bit tricky, okay? So one way to do it, okay, is what we call sunspot equilibrium. It's the idea that we collaborate through a what we call public random device, this technical term, which means that every firm make the decision based on look at the sun today. Okay, each firm compete, but every day they look at the sun. Okay, and the sun is a random variable from 0 to 1. Okay, and later turn out to be we collaborate through this kind of random device. Okay, what we're going to do is the idea is we will set the monopoly price, okay, 1 as collusion. If we punish one, we will set 0. And then we punish for T period. And how can you get punished is based on this cutoff. And what the strategy here? Let's see. Okay. The idea is the following. Okay, at the beginning of the game, you collaborate. Okay, and if we have collaborated before, okay, we still collaborate. Okay, and if we get 0 profit, okay, but the sun is still good, then we collaborate. If my profit is not good and the sky is not bright, okay, sky is still bright, then you collaborate. Okay, let me repeat. Okay, so you would collude at the beginning, and if you get profit, you still collude regardless of the sun. Okay, if good outcome, don't care about the sun. If outcome is bad, look at the sun today. If the sky is bright, do still collude. Okay, if the sky is bad, then you will punish, and you punish for T period. Okay, let me repeat the structure. Okay, let me write down here. This is, I think it's easier. So when you would collude first at the beginning, you collude. Second, if my profit is high in the last period, then I collude. If my profit is 0, my profit is 0, okay, then I look up the sky. Okay, if the sky is bright, then I continue collude. Okay, I take. If the sky is cloudy, then I no. Okay, and I go to punish for T period. Okay, after T period, I go back to normal. Of course, if there anyone that is deviate, then I go back again. Okay, I punish again. And you can check this if patience enough, you can support this outcome. Okay, I'm not going to detail of here, but what is the main supporting thing here is, okay, how can you support this collusion? Okay, is you look at your outcome, look at your profit, you keep colluding. If the outcome is good, right, you still get profit, you still do it. When you do punishment based on some collaboration based on sky, which we observe at the same time. Okay, because look at the sky is both you and opponent, we see it. The sky is bright. Okay, we forget the past. If the sky is not good, we go to the bad one. Even though it is, you may think this punishment is not perfect, but this is the best thing we can do, right? Whether the punishment will happen depend on the nature. Okay, it's not something that you can decide. Okay, because everyone can be optimistic. Okay, even though this case, right, say the sky is bad. Okay, but actually everyone is doing the right thing, but we still keep on the punishment. And actually that exactly what happened in many cases in the old world or the classical world, right? How you decide what to do is try to go to religious, right? Go to throw a coin, roll a dice, right? So you 商朝的甲骨文, right? Those random thing, right? You do random thing and decide what to do, right? The reason is because like this, right? Because we don't observe the whole outcome. Okay, so how can we decide whether bad thing had happened or not? We don't decide. We let the nature to tell us whether we continue or do the punishment. And in that case, we are able to fine-tune this beta power strategy, right? Then we can sustain our collaboration, right? Because we don't know whether it is going to be right or wrong, but we just make this kind of beta, okay, so that we decide whether to punish or not. There's a device that you can go back to. Is that okay? Of course, I agree this is a little bit difficult for you to absorb, but I think unless you actually work on this problem, you don't really need to worry, right? But I think the idea is important, right? Because the idea is like you have a device there. We try to look at it. If the state is good, we say, okay, we forget about what have been happened. Okay, so you imagine this is that like forgiving device, right? So whether you forgive him or not depends on the outcome, right? So I think this is something you also seen this, right? In the old movie, right? A girl think whether we want to forgive the boy, look at the flower, push one petal, forgive him, don't, yes, no, yes, no. At the end, yes or no, right? It's like it just make this to the, the name of God, name the nature, this is the same idea here, right? You don't make a decision, let the nature decide. Okay, so in that case, why is the case? Because it means that when you deviate, you have to have some probability that you get punished. That's the main idea. Okay, though then you would, you would try not to deviate, right? Because try to keep track, right? Because you're always tempting to deviate, right? But now when I saw deviation, if I always punish, then it can't work, right? Because nature can make you deviate. But I just probabilistic punish, then I still remain some punishment there. Okay, that is the way that to compensate the imperfect monitoring, is to use the nature to allow probabilistic punishment. Of course, you will say the punishment doesn't align with what we do, but that's the best thing we can do. Okay, of course, one thing is, okay, we allow this public device. Okay, what happens if we don't have this? Okay, that will become another research question. Okay, but we don't go to that. Okay, if you want, you can check out the book. I put in the, I think I put a book list there that you can check out, but I don't think our class will cover that. But that being said, this is also a very important piece of work. Everyone want to work on price war with imperfect monitoring. This is the paper you go back to, right? So these two are classical paper. If you ever want to work on this problem, you should read those papers. Okay, but I think I give you the main idea of this is you have to have an imperfect punishment. Okay, and the punishment whether to execute depends on nature. Right? If nature okay, then we forgive him, right? Otherwise, I don't know, right? That is the idea. Is that okay? Yeah, I'm sorry for missing the, I think, go missing. I should have get it back. Is that okay? I have 10 minutes, but I think it's sufficient for me to talk about this one. So don't worry, it's going to be short. Is there any question? So don't worry, this is going to be easy. I think 10 minutes sufficient for that. Is that okay? I understand that the last one is a little bit, I just skip too much, but if I go over that, I will spend a lot of time. But I guess I convey the main message there. So, so don't worry, this actually is not that difficult. Okay, this one is easy. Okay, and in terms of idea, okay, and you can see this application, even without going to there, one important application is auction. Okay, so that's why I would say the idea is very simple, but the math will be very challenging. But luckily, we don't do difficult math here, so it'll be simple. Okay, but if you're really actually doing serious research here, the math can be challenging. Okay, but let's look at this thing. Okay, so far we focus on the case as no agent have information advantage. Okay, in before we talk about uncertainty in the level of nature design. Okay, in the game of boom and bust, right? Nature design, and then we know it. Okay, or in the case of the before the price war, it's still more or less you know most of the thing, right? But now in the case where we know everything, no player have information advantage, is not quite right in many situations. Okay, so incomplete information means that there are certain aspects of the game player doesn't know. Okay, so we consider this, for example, Kulu defect, right? And in the complete information means that we know all the action, all the payoff, right? But there's a situation that, okay, I know my cost. I don't know the other opponent cost. How can I do the decision? Right? In the Column model, right? Here I have a C have common C here, right? But it's possible that I have C1, the other guy have say C2, right? And I actually don't know his cost or her cost. How can I make the game? Okay. If I don't know what it is, right? How can I model the game, right? Because I don't even know what is the deviation. Okay. How do you solve this problem? Because I don't know, how can we solve the game? Because I don't know, then what's going to make? So what is the breakthrough of this is passing what we call imperfect information. It's not you don't know, you just don't know which. Instead of talking about you don't know your competitor cost, you just say your competitor cost is from either 5 or 10. Okay, suppose your cost of production of a good is 5, you know is your 5. Okay, instead of say I have no idea of this, you would say we have some belief over C2, right? Maybe uniform over 0 to 10. Okay, we make assumption on what your opponent is. Okay, then allow the nature to decide what is this. Then we can solve this model. Because we change it to the game, we allow an agent which called nature. The nature decide what is the cost structure of firm 2. Okay, so that is the idea. Let me repeat. It's not that easy to see because this is a breakthrough of this whole game theory, right? Because before him, no one actually think about this. Okay, so the main idea is the following. Okay, instead of talking about I don't know what my opponent cost is, what we have is we make the conjecture, okay, about firm 1, make the conjecture about what the firm 2 is. Okay, of course, firm 2 know where exactly he is, but firm 1 would just think in terms of probability over what kind of thing they can realize, and that firm 1 knew how to do. Okay, but of course, there's a problem of firm 2 will have to know how firm 1 would think about himself, right? So there is a other issue there. Okay, and our analysis focus on what we call common prior. Okay, this is the prior in terms of Bayesian idea, right? Prior, posterior, and prior. Okay, so common prior means both firm 1 and firm 2 agree. This is what firm 1 think about him. Okay, of course, firm 2 would know exactly what she is. Okay, but firm 1 would have guessed what firm 2 is, and this prior probability is known to both parties. Okay, of course, you would say, what happens if they don't have common prior? Okay, that is something very complicated that is not we talk about. Focus on the case both of the agent would agree what firm 1 think firm 2 what can be. Okay, we'll be more precise. Okay, and here we have different costs, right? So in general, not just payoff, what about also action? Okay, because uncertainty also can not only just on cost structure, but also based on say production capacity, right? How much firm 2 can produce as well. Okay. So so we use the type, right? What type to present what the private information firm 2 would have, and we call belief to present what possible type that a player would have. Okay, let's see the example. Okay, as we said, we call common belief or common prior is the following. Okay, this is the joint probability for each type. Okay, so this is common prior. Okay, and this model do allow your belief depend on your type. Okay, which means that if I'm high type, it's possible that, say, suppose here firm 2 has low cost. Okay, and it's possible that if I'm low cost, my opponent also low cost, can be correlated. Okay, and can be other way around. It can be if I'm low cost, the other guy can be high. It's also possible. Okay, it can be dependent. Okay, so you can use Bayes' rule to derive if I am this type, what's the probability of other type. Okay, so the common prior means that the joint probability is same for everyone. Okay, what does that mean? It means that it do allow that I think I'm firm 1. I think firm 2 has high cost with high probability. Okay, but firm 2 can think firm 1, firm 2 has high cost of 1/3. Okay, we need not be agreed. Let me repeat the statement. Suppose there are 3 firms. 1, 2, 3 here. Okay, firm 1 can think firm 3 has high cost with probably 1/2, and firm 2 can think firm 3 probably 1/3. It's okay, need not be the same, because depend on what he has. Okay, so they need not agree. Okay, this is still the price, but they do have the same overall. Okay, if this is not the same, then yeah, that paper on that, but that is very complicated. Okay, is that okay? I mean, I'm pretty sure it's very abstract. So let me have an example. Okay, and because it's a static game, that the game is not complicated, right? Because you just choose action once and for all, right? So the game is like the following: is the player set and okay, payoff U, strategy S. The difference is T and P. Okay, T is a type, and P is belief. Okay, so and your type is telling us what the type can decide what kind of action you take and what the payoff. Okay, it's very general, right? And your belief is derived from that one, right? Because derive the common prior, the P. And your strategy is this is very important. Your strategy depends on type. Okay. So although you only have one type, but your strategy have to specify for all possible types. In this case, okay, firm 1 strategy is simple because firm 1 he knows his cost. He just have one strategy. But firm 2, his cost can go from 0 to 10. You need to tell the strategy have to tell me for each value of the cost what is her production. So it's a function, right? It's to specify action for each type. Okay. Okay. You can imagine that actually is like the nature is a 2-stage game where the nature move is like this. It's like subgame perfect idea. It's like at the beginning, the nature would randomize over decide what is cost of 2. And then, okay, firm 1 will choose, and then firm 2 will choose. Right? Of course, there's a information set here. And because you have to choose for every subgame, right? So that's why here. So you can consider this, in fact, is a subgame perfect equilibrium if you think in this way, right? Just the nature Here is not a strategic, but he randomized over possible C, right? Based on the prior, right? But anyway, let me quickly, although this looks not very easy, but the definition of the Bayesian Nash is very simple. Okay, it just simply means you are choosing a strategy that maximize your expected payoff. That's it. Because you would evaluate your strategy, okay, based on different scenario, right? But if say depend on which opponent you're facing, right? So let me read this, okay? This is Bayesian Nash if your strategy, okay, is you're choosing, I do the pure strategy version, you choose the maximum, the best action that maximize your utility, okay? You're holding other guy's strategy, you choose your action, okay? Based on your type T, okay? And this set type T, right? Then you have your own type, okay? You randomize over all other people types, okay? And I guess this is still very abstract. Can I go over this example? Give me 5 minutes. I'm sorry for that. Because after this, then you know how to understand the logic, okay? So the model is very simple. You only have one guy is information asymmetry, so exactly this guy. So firm 1 has marginal cost C. Firm 2 has 2 costs, high or low. Okay. And everyone will agree. Firm 1, the belief is theta is high, 1 minus theta is low. Okay. Firm 2 exactly know where he is. Okay. If the nature decide, the nature decide where high or low. Okay. And okay. So how do you solve this equilibrium? Okay. Remember, firm 2 has to decide based on the cost, what is his action? Okay, so it will be firm 2 will say, if I'm low cost, this is my production. It's my high cost, my production. But firm 1 only one thing, just one production level. Okay. So if it is high cost, this is his payoff. If low cost, this payoff. The difference is this guy. Okay. So what we're going to do is same, right? It's static game. Find the best response for each type. Okay. You can solve this. This is the best response for type 2. This best response. Sorry, for high type, this is low type. Maybe let me draw the diagram, maybe easy to understand. Let me do it quickly. So, like this. Hope you still remember this guy. Q1 and Q2 here, right? So, what is being here is you have now minus low of 2. Okay. And you also have means that you have 1, now you have 2, right? If low, you do this, high, do this. And firm 1. What firm 1 will do is he is thinking he will meet the low type with theta, high type with theta, low type with 1 minus theta. Okay. And you just basically solve this optimization problem. And at the end, okay, you will be doing something like this. best response. So let me draw it here. Is this is A minus C over 2. Yes, this is fine. And this is A1 is 0. Let's see how can I write that. So I don't know how to write here, but so here is Q1, okay, is responding to the average of these two, okay, and let me put it this way. Minus the average of this, okay, somewhere here. Yes, that's right. Okay, so and it turned out, okay, this Q1 will be I don't know, say is somewhere in the middle, okay, and that would be the payoff, okay, and you can see if the cost, you think the cost is high, you would produce less, okay, so I'm not going to we can go back to here later, but next time. But I think you can see solving this game is not complicated in the sense that it's easier to play the game, right? Because mainly you just basically try to see maximize the payoff based on your belief, right? And that is, and the belief is given, so it's not something complicated. But here is easy because here only one guy have incomplete information. But if the other guy have incomplete information, then you still need to solve a complicated fixed point. I guess I should end now. I'm sorry for overrun for 10 minutes. We'll talk about this next time. So I will, because we're done with the game, so I will put the assignment there. Maybe yeah, I'll put there. Okay. So maybe I give a longer deadline. Okay. Yeah. I see you next